In this project, I create two nodes to simulate the IoT and the Edge server, and connect them together. We use the AlexNet to do the imaging classification, and it has 13 features. So we can split the 13 features as the color points. So the color points is from 0 to 13. So at the beginning of the experiment, we install the Python and the package used in the project, and also download the data from the Cocoa dataset. It's the same as the NAP3 used. So for the beginning of the at the beginning of the experiment, we need to store the Edge server. Here I use the flags to do that. Now the server is ready to receive the data from the IoT device. For the project, we have 5 files for the classification simulate computation, and 2 files for the test. The test files for the test for the 50 images on both nodes, and the test local file only used for testing the test for the AlexNet in the IoT node. The helper files used to load images, tensor serialization and deserialization. The AlexNet partition file is used to split the 13 features to IoT side and Edge side. The IoT client file is used to run the feature before the cut point and send the results to the Edge server. And the Edge server file is used to receive the data from the IoT device and do the rest of the partitioning, and also do the rest computations and get the result for classification. So now we test only for one imaging at cut point 3. You can see when we got the result on the IoT nodes, the Edge also receives the data from the IoT nodes and feeds the rest of the computation and also get the result. So there it shows the local compute time and latency, bandwidth, and computation total time, total computation time. So now we're going to test for the 50 pictures only on IoT nodes. So the IoT nodes fully run the AlexNet to get the classification result. So we use the test local file to do that. So now we got the result. So the average floating local inference time is around 42 for the 50 images classification. And now we test for the 50 images on 2 nodes. So it takes a long time. Just cut it and see the previous result. So here's the previous result I did before. And here's the results for the running on both nodes. So we can see, based on the table, we can see the 15 images average local computation time increase as the color point move. When the color point equal to 0, the average local computation time is almost 0. And that is close to the time is 0.11, and that is close to 0 because the IoT does not run any features of the Alex Night. When the color point moves, the IoT begin to run parts of the 13 features of the Alex Night. From the color point 0 to 4, the computation time difference is small, and after that it's increased more. So the IoT takes more features to run, the average local computation time become longer. For the latency, we can see from color point 0 to 13 is decreasing, and the best latency is at the color point 13. For the count point 0, the average latency is around 75, and for color point 13, the latency is around 52. So it means if the IoT node take more features to run, the total end-to-end time will decrease. For color point 7 and 8, 9 and 10, 8 is better than 7, 9 is better than 10. It doesn't mean DNN partitioning perform worse. It's because a different color point may affect the intermediate tensor, and cause processing time a little bit different from for the closer count point. But overall, the latency show a downward trend. Therefore, it demonstrates that the total processing time for classification can be reduced if we use DNN partition method. For the boundaries, when the color point is 0, the boundaries is 603,689 bytes. That is larger than the color point 2 and 3. It shows that some color point may even be larger than the original input, but the overall trend of the boundaries is still show decreasing. The smallest the boundaries is at the color point 13. Therefore, it means the early color point will expand the data transmitting size, and the later color point may decrease the transmitting data size a lot. So for the total computation time, we can see when we running this project on two nodes, both nodes, we can see the time is also decreasing. For the color point 0, 1, 2, 3, 7, 9, 11, 12, 13, the computation time show a decreasing. The worst computation time is around 60. Is around 60. The count position, the count point is 0. The computation time show that the total computation time can improve by the DNN partition method. So based on the experiment, when we use DNN partition, the local computation time is increased with the call point increasing. The boundaries decrease when the call point move closer to 13 because the local IoT does more work on partition parts, and the compressed results are sent to the edge nodes. The latency is also improved when IoT take more computation for DNN partition part. In addition, the total computation is also improved as the call point move closer to 13. Therefore, when the call point is 13, the system has the lower latency boundaries and the total computation time. If we compare the DNN partition with the following local IoT Alex Knight process, we can see the full local inference still perform better than the running on the both node. This means the IoT node in the cloud lab we set is enough computation power to support the Alex Knight, but in the real world, the IoT like the security camera may not have enough computation power for the classification. So the DNN partition can improve latency and boundaries and computation time. Therefore, the DNN can be used to improve the problem of the IoT device lacking the computational power.